Hello everyone and welcome to another lecture. Today we want to talk about another kind of linear operator that will be very important in our study of physics, that is called unitary operators. An unitary operator is defined as, so let's take the definition first, and it is defined as U dagger U equals to identity is equals to U dagger, where U is our unitary operator. Now this might seem a bit weird because what is so special about this thing, right? So to motivate you, I want to show you the Schrodinger equation. The Schrodinger equation is an equation that can be written as follows. And here I'm taking a notation where h cut equals to 1. The significance for this is that you are measuring, if you compare this equation, is equals to h cut omega, I believe. Yes, because omega by twice pi is equals to just f. So when you take h cut equals to 1, you are measuring energy and frequency in the same scale. So this some frequency will correspond to some energy. So this is just I ddt of, and state, recall that we called this get vector state in one of our lectures. This will be given by a Hamiltonian operator acting on the state. And the solution of this state, and since these are time dependent, the solutions will come off as this, where this is some initial state. At t equals to 0. And this guy over here, that is this exponential, and it has an operator. Notice that this is not a number over here. Rather, this whole thing is an operator expression. Now you may not understand this, but that's not the point. The idea is that this operator is actually a unitary operator. So this is one way to motivate the importance of this unitary operator, but this is from the point of view of quantum mechanics, but we will also try to see why these are important in the perspective of linear algebra. So the next thing we will do now is that we want to provide another motivation to study them, and this motivation comes from a theorem. So let's write it down. Theorem. Oops. This theorem says that an unitary evolution, or so to say, when you have unitary operators, they preserve the inner product between the vectors they act on. So what does that mean? Let's say, okay, so let's first write it down. It's also motivation for us why we want to study the unitary operators. And let's write some unitary operator u. Okay, let me just choose another color so that so let's say we have a vector b prime which was originated from v through a unitary transformation. That is, you have this v, you plug in this unitary operator u in front of v, and you get another kid v prime. So what will be this bra? We remember that the bra of v prime will be given by the dagger operation, or so to say the adjoint operation. So if you do that, this will be u v kid whole dagger, and the ultimate thing will be bra of v and u dagger, right? And now you ask, what is v prime? V prime, that is the inner product with it, right? This is quite easy. So you just have to write v u dagger, and from here, that is this part, let me mark it down, this part will give you u and v, right? But u dagger or u dagger u, according to this definition, is just the identity matrix. So you write v identity v, and identity acting on any of this, that is, it can act on this or it can act on this, it doesn't matter. For our convenience, let's just act identity on this vector, that is the cat. So this will only be v, and you can see that the inner product for v prime is the same as the inner product for v. So this is a very important thing to notice. Why? Because this tells us that, so what does this tells us? Okay, let's write it down. This tells us that under unitary, we are calling it an evolution, but you can also call it transformation. Under unitary evolution, the inner product of a vector is invariant. And you will see why this is so, because you can see that from this quantum mechanical example that the inner product with psi and psi, this psi, that is the time after the evolution of time, this psi thing, let's mark this down so that you can understand it. This thing, that is, this is just equivalent to this, because this guy is some u, right? And the inner product will be the same. So this will correspond to some scalar, something invariant that is not changing. All right, and okay, so this is one reason to study this unitary operators. And now we want to see some explicit examples of unitary operators. The idea is the same. Let's say you have a matrix, let's say call it A, and this is given by this. And A dagger will be square root over half. Remember, the dagger operation is traced out by traced out, I mean, is done by first you transpose it, or first you take the complex conjugate of it and then you transpose it. So if you do that, this will be just this thing, right? And if you multiply A dagger, you will have 1/2 over here, and you will have this 1 I1, 1 minus I, 1, and you have 1/2. This will go with this, so this will have 1, and this is I squared, and there is a minus in front, so this will give you 2. Similarly for this, it should give you 2. Oh, not sorry, it's not 2. It will give you a 0, because this is 1. Okay. Sorry, this is the minus I, right? Yeah. So this will be minus I, and there will be a plus I, so that will be a 0. And then you will have a plus I, and there is a minus I, that will be another 0. And there you will have minus I squared, that is 1. And you have 1 times 1, that is 1, so it's just 2. You can bring out this 2. And finally, you can write this as 1, 0, 0, 1. And unitary operators have more nice properties. That is, if you transform a matrix in such a way, let's say A prime is something that is written as u dagger AU, then you can show that trace of A prime will just be trace of A. Also, the determinant of A prime will also be just determinant of A. And these things are basis independent quantities that you can calculate from matrix. So if you want to say it in a fancy manner, you can write physics is unitary. Whenever you have non-unitarity, you can always be sure that there is something is wrong. So this will be it for today, guys, and I'll see you guys on the next lecture. We have only touched the surface of unitary operations, but you will know much more about it when you take a quantum mechanics course or a quantum field theory course or any high energy physics course. So thank you.